right, now we're going to talk about section 7.2. And section 7.2 is where we actually get to formally define probability. So let's do it. For a sample space S with equally likely outcomes, here it is. The probability of an event, E, is as follows. Well, I'll say occurring, is, okay, so the way we write the probability of event E is this is how we write it, P of E. So this says the probability of E. By definition, it's equal to the number of elements in the event divided by the number of elements in the sample space. Okay? Clearly, we cannot have an empty sample space because it's illegal to divide by 0. Okay? So, when you want to talk about the probability of an event, what you do is you count the number of elements in the event divided by the number of elements in the sample space. All right, now I want to make a quick comment here. I want to tell you that the probability of any event is always between 0 and 1. So if you're ever computing a probability and you get a negative answer, you made a mistake. Similarly, if you ever compute a probability and you get something greater than 1, there's also a problem. Okay? Now, when we talk about our probabilities, in general, we keep them as either fractions or decimals. I understand that sometimes various probabilities are given as percentages, but in this course, we always like to put our probabilities either as a fraction or a decimal. So that's a really important thing to keep in mind. Another important thing to keep in mind, while it is definitely a polite thing to reduce your fractions, in this course, I'm okay with you not reducing your fractions. Okay? All right, so what I want to say is, all right, I made this claim that the probability of an event is always between 0 and 1. And let me show you why. Okay? So, let's talk about what is the smallest type of event we could have. Well, couldn't we have an event that was equal to the empty set? For example, that rolling a die example that I gave in the last section when we talked about the event of rolling a number greater than 9. Okay? Well, will you agree that if my event is equal to the empty set, the number of elements in my event is 0? All right. Well, if that's the case, then if we talk about the probability of E, well, it's the number of elements in E divided by, who cares what, the number of elements in the sample space, and 0 divided by any non-zero number is always 0. That's why the smallest our probability can be is 0, because the smallest my event can be is the empty set. On the other hand, let's talk about how large an event can be. Well, the largest an event can be is actually just equal to our sample space. Okay? Remember, when we're talking about various experiments, our sample space becomes the universe. It is the set of everything. So, if my event is equal to my sample space, I think you'd agree that obviously the number of elements in my event is equal to the number of elements in my sample space. In which case, if I want to talk about the probability of this event, well, by definition, it's the number of elements in the event, which we know is this, divided by the number of elements in the sample space. And what is any number divided by itself? It's equal to 1. Okay? So that gives you kind of the background as to why our probabilities always have to be between 0 and 1. All right. other little comment that I want to make here is the following, okay? When we talk about various events, okay? Okay, my whole sample space is right here. Remember, we liken that to our universe. So I think you'd grant me, if E consists of everything that lives in this circle, E complement consists of everything outside of the circle. Remember, the complement of a set is everything in your universe, i.e. sample space, that's not in that event. So we know that if we take E and union it with its complement, we get everything. We'll call that S, right? I mean, everything in E joined with everything not in E gives us everything, okay? Now, let's also talk about what the probability of our sample space is. Well, we pretty much did it over there. If we want to talk about the probability of our sample space, that's clearly equal to 1 because you take the number of elements in the sample space divided by the number of elements in the sample space. So the probability of everything is 1. So something that you can get from that then is that the probability of an event plus the probability of its complement is equal to 1. And this actually turns out to be somewhat useful at times, okay? Because sometimes finding the probability of an event might be quite difficult, but you can find the probability of the complement with relative ease, okay? And if that's the case, you can do a little algebra here, just subtract the probability of E complement from both sides, and you get that the probability of an event is 1 minus the probability of its complement. Okay? This is another formula that turns out to be really quite useful. Okay, so let's just go back to our dice example and play around with a few probabilities there. And let's begin here. So, suppose a fair die is rolled. And let's find the probability of, how about rolling a number greater than 2. Now, if it helps to write out the sample space, absolutely do it. Okay? All right. Well, by definition, the denominator is always the number of elements in my sample space, which is 6. And now what we want to do is find the probability of rolling a number greater than 2. So what we do is we look in our sample space and say, all right, how many numbers in here are greater than 2? And I think you'll grant me 3, 4, 5, and 6. So there's 4 possible ways of rolling a number greater than 2 over the total number of ways there are. So I would write that as 2/3 because I like to reduce my fractions. If you leave it as 4/6, that's fine. If you'd like to write it as a decimal, that is also fine. All right, so what is the probability of rolling, boy, I don't know, an odd number? Well, again, total possible outcomes, there's 6 of them. How many odd numbers are in my sample space? There's 3. So the probability is 1/2. Okay. Next, let's talk about cards. Cards are a fun example to use in the next couple of sections. In case you might not be aware, there's 52 cards in a deck. 26 of them are red and 26 of them are black. Okay? Another thing that you need to know about cards is that there are 4 suits. 2 of them are red, 2 of them are black. So, Our red suits are hearts, so there's 13 hearts and 13 diamonds. There's also 2 suits that are black cards. And again, there's 13 then of each of them, and those are spades and clubs. Okay, so the other thing I'd like to mention about cards is we have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we have jack, queens, and kings. Okay? Now, with cards, let's just take 10. You're going to have a 10 of hearts, a 10 of diamonds, a 10 of spades, a 10 of clubs. You know, with any of those cards, you have 1 of each suit. So there's 4 of each type of card. Okay? Some particular cards that we discuss in this class are what's called face cards. Those are our jacks, queens, and kings. Okay? And we have a jack, queen, king of hearts, jack, queen, king of diamonds, jack, queen, king of spades, and jack, queen, king of clubs. Therefore, there's 12 face cards. All right, having done that, let's find a few probabilities here. All right, so what our experiment is the following. A card is drawn from a standard deck of 52 cards. Okay? Clearly, we are not going to write out our sample space here. The important thing is that our sample space has 52 elements in it. Okay? So, let's find the probability of drawing a red 9. Well, again, there's 52 cards in the deck. How many red 9s are there in the deck? There's 2. If you want to simplify that and write it as 126, beautiful. All right, what if I want us to find the probability of drawing a 2 or a red queen? Again, our denominator is 52. All right, how many 2s are in our deck? We have 4 2s. And we have 2 red queens, therefore we have 6 over 52. All right, let's find the probability of drawing a red face card. Okay, again, our denominator is 52. All right, let's go over there. We have a total of 12 face cards, okay? And as we see, everything's divided in half with our cards, half are red and half are black. Therefore, if we want to talk about the number of red face cards, it's half of that 12, or 6. Okay, so let's look at a couple other examples here. Suppose we have this. I'm going to do a couple table questions. All right. So suppose we have, I'm going to do a table, show you a table based on blood types. And what I want to do is do 2 different types of tables that you might come across and show you how to approach each different scenario. So what this problem reads is the following. It says the percentage of the general population that has each blood type is shown in the following table. All right, so we have blood type and we have population in terms of the percentages. And our blood types are A, B, and O. And what we're given is 41, 12, 3, and 44. Okay, so what they want us to do is give the probability distribution. In other words, figure out what the probability that a randomly selected person from this population, what the probability is that they have a blood type of A. And again, for each of these members. So, the moral of the story is this. When you're given the percentages in a table, you should be totally psyched. Okay? It's really all given to you. Now, notice, if we add these four numbers, we're going to get 100%. Because the whole population in its entirety is going to have one of these four different blood types. Now, in a similar manner, like your percentages have to add up to 100%, when you're doing a probability distribution table, and that's something that we're going to discuss further in Chapter 8, one of the things you have to keep in mind is just like the sum of all of the percentages is 100, the sum of all the probabilities has to be 1, because everything put together has got to give you your sample space. So, what I want to say to you is this. If you're given the percentages, all you have to do is change each percent to a decimal, okay? You could put each of them over 100, that's equivalent. Recall, in order to change a percent to a decimal, you just move the decimal point 2 places to the left. So, you get 0.41, 0.12, 0.03, and 0.44. Okay? Celebrate that situation. All right. So, let's talk about another type of table that you're going to come across that does involve a little bit more work. Okay? In these tables, you're not given the percentages, you're given the frequencies. So, for example, well, let's take this example out of a book. It's kind of a silly example. I'll write down all of the relevant information for sure. It's called checking into a hotel room. It says in a survey of 3,019 hotel guests, the following question was asked. What is the first thing you do after checking into a hotel room? The results of the survey are as follows. So, one activity is adjust the thermostat, and 1,027 people said that. Turn on the TV, 755 people said that. Unpack, we have 634. Check out the free toiletries, so free stuff. 211 people said that. I'm going to put lines here so that we can distinguish. Plug-in rechargeable items, 60 people said that. Find the gym, we have 30. And something other than those, we have 302. Okay? All right, so notice here we're given the frequency or the number of respondents. Okay? So there's nothing to change over to decimal form. So what I want to ask is the probability. Suppose a person is selected at random from the list of the 3,019 guests surveyed. And we want to find the probability as a first activity that they adjust the thermostat. All right. Well, what's the total number of responses that we could get? In other words, the total number of elements in our sample space? 3,019. Okay, so now we're going to start seeing why we very often don't list our sample spaces. So, you take the total number of people queried, and then you say, well, how many people said adjust the thermostat? 1,027. And that's that. Okay? How about we want to find the probability that they unpack or find the gym. Again, your denominator is the total number of people questioned. And my numerator is, well, there's 634 people that will say unpack, and there's 30 more people that will find the gym. Remember, or means add, so we're going to have 664 people. Okay, well, that finishes section 7.2. Thank you.